Hello and welcome to this video. In this video we're going to be looking at the topic of fluorescent tubes. So sometimes they'll call this the collisions of electrons. So we're going to be looking at, we've already looked at a lot of how photons can cause energy changes in an atom by essentially electrons absorbing the photons, absorbing all of the energy that they hold. But we also said the other way that they could gain energy would be from collisions, okay? So that's an example that we're going to look at in the idea of fluorescent tubes. Okay, so a fluorescent tube, you've probably all seen one, even if you aren't familiar with the idea. It's like those very long light bulbs. So you have one end, you have a long light bulb, and then you have the other end, essentially. Okay, in one side you're going to have a filament. Okay, we're going to call this the cathode. Okay, and there's going to be a potential across this. The cathode we know is negatively charged, so the anode over here is going to be positively charged. And this whole setup, the idea of it is that inside the fluorescent tube we have mercury vapors. Okay, so very faint gas mercury molecules. It's not going to be full. This is why we call it vapor. It's not just mercury gas. It's just small amounts of mercury gas to undergo those collisions, but we don't want to have loads of it because then we won't have enough time for the electrons to actually gain enough energy to be able to excite the electrons in the mercury. We also have what we call a phosphorescent coating. So phosphorescent coating. Let me try that again. Coating. There we go. And it's just phosphorus that has been coated on the outside, and we'll see why that's necessary in just a second. So there are three major stages to fluorescent tubes. The first one is starting at the cathode. Okay, so the first thing is thermionic emission. Okay, so thermionic emission is how we're releasing the electrons in the first place. So we've already seen in the photoelectric effect that when the material absorbs enough energy, the electrons can absorb that energy and then they can release electrons from the surface. The same thing is going to happen in thermionic emission. This cathode essentially acts as an electron gun. And what happens is we put a very high potential difference across it, which means that we've got loads of electrons colliding inside that inside the filament. So large amounts of electron collisions inside the filament causes it to heat up. So it heats up, and then the electrons absorb the energy. I'm just going to call energy E, and are emitted from the cathode. Okay, because they have enough energy to be emitted. If they don't have enough energy, then they basically just have to wait a bit longer for the temperature to get bigger so that you've got more thermal energy to be able to absorb, and then you can be emitted after that. So the first thing we have is thermionic emission that's emitting electrons down this tube. Now the idea of the anode here is the anode is going to accelerate this, okay, because the electrons we know are negatively charged, anode is positively charged, so this is going to be accelerated along this tube. As it's accelerated along, it gains energy. Okay, so let's actually have another stage in here that's going to be a little bit of a smaller stage. So we have acceleration. Okay, so acceleration, the anode accelerates the electrons, and they therefore gain kinetic energy. Okay, this all happens until they collide with a mercury atom. Okay, when they collide with a mercury atom, so stage 3, if I can fit it down here, is collisions with the mercury vapors. And so let me just get rid of the title there. What happens when they collide with the mercury vapors is the electrons collide with the mercury atoms. Then the kinetic energy is transferred to electrons in the mercury, and so the mercury is excited. I'm going to continue this up here. So this is 3 continued. So we've accelerated the electrons, so they gain loads of kinetic energy, and then they're going to hit a mercury atom, and they obviously repel the electron. So if they're going to come in and collide with the electron, it means that it's going to start pushing that electron away. In doing that, you're basically giving it more energy because you're pushing it, and so by pushing it, you might possibly completely ionize the mercury, in which case just an extra electron comes off the mercury and travels down the tube, which is completely okay because it's just going to increase the current traveling around. Or it could collide with an electron and or collide with the atom in general and cause an electron to gain enough kinetic energy that it jumps up to a second energy level. That's why it becomes excited, because it gains all of that kinetic energy from that collision. And when it gains that kinetic energy, becomes excited, we know things aren't very stable when they're excited, so it de-excites and it emits. So the mercury de-excites, and it actually emits UV photons. Okay, so photons with a frequency so high that we can't even see it. Okay, and that means they have a lot of energy. Now, the whole idea of a fluorescent tube is to act as a light bulb, and if it's emitting light that we can't see, it's not very effective as a light bulb. So we need to fix that problem, and that's where the phosphorescent coating comes in. Okay, so the reason the UV photons are produced are because the energy levels in mercury have a very large gap between them. So the one jump down to the ground state will have a very large energy difference, and so it will have an energy that will produce a UV photon. Okay, let me just change this slightly, and then we can look at the last stage. Last stage is the phosphorescent coating. So the phosphorescent coating, and what that is there for is to absorb those UV photons. So the phosphorus absorbs UV photons, and then obviously gets excited, so is excited, and we want that to de-excite as well because it's not going to be very stable. But when phosphorus de-excites, the gaps between them are much smaller, and so it will do that. It will take in the whole UV energy, but it will then release it in smaller gaps, almost like in stages, and so then the phosphorus releases light that is visible light. Okay, so this is visible light. Okay, and so that's how we see the light from this lamp. Okay, it sounds like a very complicated process. We actually don't use these fluorescent tubes anymore because we know mercury is a toxic vapor, so we don't like putting them up everywhere. So we don't use these anymore, but the physics behind it, the idea behind it, of the collisions with electrons can also transfer energy and cause photons to be created, is another important point. If anyone is interested, there's also a phenomenon called Compton scattering, which follows this kind of same idea. where a collision with between two electrons is going to cause a photon to be emitted. And you'll get to that at higher levels for anyone who wants to go on to do physics or maybe even engineering at university. Okay, so fluorescent tubes, as a recap, we first initially have thermionic emission, electrons emitted from the cathode. The electrons are then accelerated across this gap, which is mostly a vacuum but has some mercury vapors in it. They gain kinetic energy from this acceleration. Then they're going to collide with the mercury vapor. They cause some of them to be ionized, in which case the electrons will just continue to flow around the circuit. They cause some of them to be excited, which are going to release photons of UV when they de-excite. Those UV photons get absorbed by the phosphorescent coating, which is excited, then de-excites in smaller stages to emit what we know as visible light, and this is why we can see the light from the lamps. Thank you for watching.